Hi all, welcome to part 4 of the video lecture on sequential circuits. See, what we were discussing is the way of analyzing a basic latch circuit which can just store and retain single bit of information. We are going to see how that storing and retaining is happening. Okay, so in the previous video, we understood how this a small circuit made up of an OR gate or an AND gate is capable of retaining an information. Now let's see the general case where the two NAND gates are being connected and the output of one is being fed to the other one and the other one is taken as a feedback to the first one. And these two inputs are being taken from the user as set and reason, and this terminology we will say later. Let the first input be A and the second input be B. Okay, so that this is my A and this is my B, and how this is working. So that is what I'm going to say. And the output, let me denote it as say Q. So this is like yeah, this one is denoted by QA. Okay, fine. Here this is represented by QB. Okay, whatever it is. Okay, you can use some different notation also, QA and QB. See, that is what we are going to see, and when it's something now it is very clear to you, like from the last video, if you understand that, you will understand when A is equal to 0, whenever I am applying a 0 here, you can see this is your OR gate. When one of the input is 0, it will wait for the other input, right? So because 0 alone I can't make a decision. So what is happening is the other input is actually your QA, right? So whatever this QA can be 1 or 0. See, if this QA is 0, 0 0, the output will be 1, right? Like that. If this QA is equal to 0, so this its complement is coming, right? If this QA is 1, this output will be 0, like that. So you can see that the output is nothing but this QB is nothing but the QA complement. Okay, so that is the way this is working. Now the other case is like see, when this A is equal to 1, so this is interesting. When this A is equal to 1, it will simply ignore this data line. I mean, this QA is fully ignored and the output is simply 0. Okay, so this is important for us, because when one of the input for this NOR gate is 1, OR gate and negation, right? So one OR gate will give you 1 and its negation will give you 0. So the output is always 0 irrespective of this feedback input. Okay, so this is interesting. Similarly here, this B. So what about this B? So when you are giving this B to be 0, so here you are getting this QB, right? And QA is found to be QB complement. So this, you think about it, this when this is 1 you will get here 0, when this is 0 you will get 1. So just its complement you will get in the output. But what we are interested is what will happen when this input is 1. Okay, so when one of the input is 1, just like here, when one of the input is 1, you can see that this QB you are applying here, you will get this QA as 0 fixed irrespective of this QB. It's simply ignoring this QB. Okay, so because the same thing I explained here, the NOR gate, one input is 1 means its output is fixed 0 irrespective of the other input. So this is a fundamental circuit, and this understanding is what is needed for us. Now let's see the detailed analysis of the circuit that we've seen already with 4 cases, because this A and B I can have 4 choices, right? So let me start with the first case, that when A is equal to 1 and B is equal to 0, I'm randomly checking one case. Okay, that's all. So this is how the user is giving the input. From the user point of view, the circuit is looking like this. So these two inputs we are taking from the user, right? And the circuit is giving you an output that is your Q. Okay, that's all. We don't know what is happening inside. Okay, so understand that in your mind. So this is the first case, that is this 1 and 0, and can you tell me what is the output of the circuit? So first thing, this is our NOR gate implementation. So what is interesting for us is this 1 case. So whenever you are applying one of the input as 1, it will not wait for the other input, right? Irrespective of this feedback input and all, whatever it is, whether you are the circuit is already containing 0 or 1, whatever is coming, whenever this is 1, this NOR gate will give you the output 0. So this is always fixed. Okay, this is what is needed for you. This is the main understanding needed. So that for that I given that last video lecture, I mean the third part of the video lecture, only I explained only this concept. Okay, yeah, whenever this A is actually the control input, whenever the control input to the NOR gate like this feedback NOR gate is 1, it will ignore the data input and the output is fixed 0. So now for the second NOR gate, this is the first NOR gate, right, and this is the second NOR gate. For the second NOR gate, you can see the input, both the inputs are 0. Both the inputs are 0 will give you what? 0 0 it's I mean you will get OR as 0 and this negation as 1. So here you will get a 1, and you can see that this is always retaining in this state. So right, because as long as this input is 1 0, the circuit will be like a 1 0 1, and this 1 will come here, right, and this 1 is what you are taking as output. So you will get the output 1. So the circuit is now giving you a 1 when the user is feeding an input A is equal to 1 and B is equal to 0. So that is a scenario, right? So keep that in mind. Now let's analyze the second case here. See what's going on here. So here let it be like the opposite case, that is here let it be A is equal to 0 and B equal to 0. Let's see what happened. And here again what we are interested is this case, because whenever for the NOR gate one of the input, see this is not NOT gate, don't be confused with that, because this is a symbol for NOT, okay, or and this is a symbol for OR, and when you are applying this, that will be NOR. Okay, so hope you are clear about this notation and this notation. Here just a triangle kind of thing. This is just like, and end with this is for NOT gate and this is for NOR gate. Okay, and OR gate is just this. Okay, that's all. So hope the notations are clear. So what we mean here is the NOR gate. These are all NOR gates. Okay, so this is my first NOR gate and this is my second NOR gate. Okay, NOR gate 2. Now let's see what will happen. And here also this is the circuit from the user point of view. User is not at all worried about what is happening inside the circuit. The user will simply give an input like a 0 and 1, and it will wait for the output. And you can see that this NOR gate will definitely work without waiting for this input. This will always give you this one. So this understanding is important. So this NOR gate will always output you this 0. And that 0 you will get as a final output, and this 0 you are feeding back, so that both inputs are 0, so the output will be 1. So here it will always retain this 0. So as you are taking this 0 as the output, you will always get this 0. So that about it. Now the next case is actually interesting for us. See this one. So it is something like what will happen when A is equal to 0 and B is equal to 0. Actually A is equal to 0 and B is equal to 0 means what? So actually this 1 and 0, 0 and 1 can be any of the input combination, and this 0 0 means both the inputs are taken away from the circuit. The user is not giving any input, something like this. So this is a default case, right? So when you, so this is your case 1. So from case 1, when you take both inputs, you will get this case 3, and this is your case 2, and this is your case 3. And case 3 is something interesting whenever the user take that input back, right? So this is something like there is no input to the circuit, right? So initially I given a 1 0, I got 1 as output, and I found like 1 is being stored and here 0 is being stored. Now A equal to 0, B equal to 0 means I am not giving any input, I just taken both my inputs back, right? So that is the meaning. And now what will happen? So this is very, very interesting. So what will happen is actually the circuit will retain the information. So here this 1 is being saved. I can say that 1 is saved, right? 1 is saved, and here I can say that this 0 is saved. Two cases, right? And what is happening here is actually it retained previously saved information, and I don't know what is the previously saved information. Okay, let me take two cases. Let me explain this fourth case also with the same input to tell you what does it mean by this. Actually I thought of explaining you one case that I will explain in the next slide. So here let's take the same case 0 0 0 0, and we don't know the retaining part. We don't know. What we assume is previously the circuit is having suppose the circuit is already holding some 1. Okay, so you know, if this is 1, this 1 will come here, and this is a case, right? So this is what happened, and you know when this will result as part of case 1. Okay, so because of this case 1, so this is sub part of case 1. And similarly in fourth case, what I need is I want it to be a sub part of Second case, I'm explaining everything in detail, so please be patient and please be careful. Okay, so what is happening, try to understand it as it is, because it's okay, I can tell you directly the mapping table and all, but I thought of giving you the correct feel of it, so that whatever combination they can ask you, you will be able to answer. Okay, so this is a subpart of 2, so that you see subpart of 2 means what. Let's see, the circuit is already containing this 0 1 0. I mean, the circuit is already having the information 0. Now the question is, when you take this input back like 0 1, you are making it like a 0 0. Here also this 1 0, you are making it 0 0. Am I able to retain the previous information? Okay, so that is the question. So let's analyze it now. So what is the thing? So already the circuit is what, having output 1. Will it change or not? That is the question. When you when you give both inputs are 0 0, will this output 1 changes or not? Here also this circuit is already contained in this 0. Will it change or not? Okay, so that is the question. Will it change to a different output? Okay, so what I promised to you is like it can retain the retained the previously saved information, like that I told you, or it simply it retains. Okay, so let's verify it. Okay, so what is happening here is the 0 0 case, and you know, when both the inputs are 0, both the inputs are 0, the circuit output is 1, right? When both the one of the input is 1, you know, the circuit output is 0, so it's very clear, right? So the circuit here, it is 0 1 0 1. What is the output of this NOR gate? This NOR gate 1, this is my NOR gate 1 and this is my NOR gate 2. Okay, so just tell me, what is the output of this NOR gate? One of the input is 1, the output is 0, right? And here both inputs are 0, the output is 1, so it is retaining. Actually this 1 is retained as it is, as long as the user input, I mean, so as long as the input is like 1 and 0, you are getting 1, and when you take that input away from the circuit, like when you so this is something I can call it as the output is unchanged. Okay, so that is important, right? The output is unchanged. The output is unchanged means what? Unchanged means the output at a time t plus 1 at any instant is nothing but that output at t. There is no change for the output, simply it retains the output. So this understanding is very, very important for us. Okay, I think let me use the same pin, same color. The output at time t plus 1 is nothing but output at time t. So that is the case. So this unchanged situation is what I am achieving. So here also let's verify 0 0, the output is 1, 0 1, the output is 0. So this 0 is also retained as it is. So what is the previous output? That will be just retained as it is when both the inputs of the circuit A and B are 0 0. Fine. So whenever you apply like a 0 0 as the input, this is how the circuit behaves. So actually 3 cases are over. The third case I explained in 2 different ways. Okay, so that about it. Now let's see the fifth case. Fifth case means when you are looking at the combination, it is actually the fourth case. Okay, because it's 1 2, this is the third case subpart 1 and third case subpart 2. So let's write like that. Okay, the third case itself, this is the subpart of 1, subpart of 2, like that I explained. Now the fourth case, let's see here. See, actual fourth case is like a, the same circuit I am having, this NOR gate and the second NOR gate, the first input, the second input, the output, right? So this is the case right now. Let me show you. This is a circuit I am having. Okay, and this is the output of the circuit. Now the what is the last case? The fourth case is like when the inputs are like A is equal to 1 and B is equal to 1, and let's see what is going to happen. And see, it's somewhat tricky actually. This is my NOR gate 1, and let me write the NOR gate 1, or let me write it like, you know, it is NOR gate 1, and this is my gate 2, right? So it's somewhat tricky. There will be different cases. Let's see it now. Yes, Let's see the subparts. Like, what is the problem here? This is actually a complicated situation. So when both the inputs are 1 1, so okay, let's try to understand what is happening. When one of the input to the NOR gate is 1, actually there is no problem, because the output is something like fixed 0, right? The output is 0. Here also one of the input is 1, the output is 0. So it's something like this. So here also you are getting zeros. Like, so here it's 0, output also you are getting like 0. So you are able to save 0, right? So here also you are saving 0. See, in the second case also you are saving 0. But can you observe some difference here? When you saved this 0, you are getting like 0 1 0. I'm just calling like 0 1 0. So in between you are getting this one. But when you saved that 0 here everywhere it is 0. But still you are able to store 0. There is no issue, right? Now, I mean, you can, when a equal to b equal to 1, there is no issue, means we can save 0. Okay, so maybe a different way of saving 0, we can interpret like that. But is it okay, right? That is my question. So is it okay to understand that? Let me ask you the second question. Can I retain this 0? So that is a question, right? It's a saving alone is immaterial for us, because you can save anything everywhere, but are you able to retain it? Then only the full purpose of saving is met, right? So in our general the way, when you are studying also, you can save, I can tell you can remember, that is fine, but are you able to retain and are you able to apply it during your exam? That is what matters, right? So here also the full purpose of saving is fulfilled only when you are able to retain it for some longer time, right? In the sense, so it's just like I'm giving you something and you are taking it, right? You are saving it in your brain, but when I'm going back, are you able to retain it? Similarly, when I applied that a equal to 1 b equal to 1, it is storing that 0. When I take that input back, like when I'm taking it back, means this 1 is gone, right? I'm taking the input back, so this also is gone. This is something like our third case means both inputs are 0. So otherwise I taken both inputs away from the circuit. There is no input to the circuit actually, right? So both inputs are 0, means there is no input to the circuit, right? So now what will happen? Let's see. So here it is somewhat so the question is like there are 3 sub cases I can think of further. So depending on the speed of this gate 1 and gate 2, let me write the first case. I mean, this is the fourth one. First case we are saying. So what I am writing is, say gate 1 is faster than gate 2. Randomly I am taking this case. So that is the scenario I am saying. So it is gate 1 is little bit faster than gate 2. So what will happen when both inputs are 0 to gate 1? It will immediately, both inputs are 0, so it will immediately give a 1. So as soon as you are getting a 1 to one of the input of this gate 2, what it will do? It will 1 and 0, it will give you one of 0, right? So this is a case, you will get like a 0 1 0 or 0. I mean, this q is equal to 0. Let me write like that. So that is the first case. Now the same circuit I am explaining in a slightly different way. The same case, initially when a is equal to 1 and b is equal to 1, the circuit is just capable of keeping a 0, right? That this q is found to be 0. Now what I'm doing is, I'm just taking this input away from the circuit, like this a is equal to 0 and b is equal to 0 is what I'm feeding. Now this fourth case, I'm considering the second category, where gate 2 is faster than gate 1. Okay, faster than that, we don't know in real world scenario whether both are equal speed also, that also we will consider, or which is faster, that we don't know. If this is the case, definitely this gate 2 will be executing first, so that this will be changed to 1, right? You can see that, and this 1 will be fed here, and here this will be 0. So that is a scenario. That means this 0 is changed to 1 now, but in the previous case this 0 is kept as 0. I mean, in this case what you can see is like this q at the time t plus 1 is nothing but something like a qt, the previous one complement, or you are getting it as 1. Here what is the case? Q at time t plus 1 is actually q at previous time 0. So I am getting a different situation, right? Same scenario I am explaining, but here I am considering different cases, like gate 1 is faster than gate 2, right? Like that I am telling you. Now let me tell you the last case also, like the fourth case, fourth subpart 3. Okay, So here what I'm saying, both the gate 1 and gate 2 are of same speed. Okay, are of same speed. So now tell me what will happen. Okay, I'm just giving everything in a little bit detailed manner, but actually fine, we will conclude soon. So here, the situation is like our fourth case, that is when both the inputs are 1, there is no issue with the circuit because it is simply storing a 0 for you. But the problem is whether it is capable of retaining this information. So the situation is like both of them are of equal speed, so that what will happen, this one of the input is 1, right, one of the input is 1, so irrespective of the other input, this will be, I mean, sorry, the case is like when both the gates are 0 and when I'm taking the input back, right, so it is something like this. So both inputs are 0, here also both inputs are 0, and this is changing to 1, right, and this also changing to 1, right, and that will fed back, and again some kind of toggling will happen. So this 1 will come here, this will change it to 0 0. Okay, the current instance, it is just like this 0 is changed to 1. So you can see that this qt plus 1 is found to be 1 in this case. Okay, so I mean, I have a kind of ambiguity, right? So in two cases I am getting 1, the last case also this 1 is not stable there, immediately that feedback may happen, and that 1 may change it to 0 also, like that 0 1 0 1, like that some kind of toggling will happen here. But anyways, is it clear? Because when I'm giving this 1 back, one of the input is 1 1, so this 1 will change. So some kind of toggling is the result actually, that continuous changing I'm saying. So anyway, at the particular instance I'm getting say 1, so here I'm getting 1, so here I'm getting 0, so that means, so actually this is 0, here it is found to be 0, but here it is found to be 1. I mean, I'm not able to retain the information, so that is the conclusion. So the conclusion of this fourth case is, when a equal to 1 and b equal to 1, the device can store 0, but it can't retain that 0, it can't retain this 0. So that is what we observed. So here it is changed to 1, right, here it is changed to 1, and in some case it is keeping it also. Okay, so again the main issue is not only that, so the retaining is a problem, and also in addition to that problem we have something called, I mean, we are getting some kind of ambiguity in the output, right? So it's not like a 1 or 0, we don't know, right? So let me write, like, we can't even know for some certainty what information we get as output, right, so it's very crucial issue actually. Storing, retaining, okay, it's not somebody is not able to retain the information, fine, but it is behaving something unpredictable, that is more serious issue, right? So I'm telling you something, okay, you forgot it, fine, but you are taking that information in a different way. To one person you are telling it one way, in another person you are telling the same information in a different way. That is not needed, right? So that is a completely unwasted thing, right? So it's a completely wasted thing, sorry. Yeah, so that is what is happening in this fourth case, fine. So we are not going to allow this input because it is a very very dangerous case, right? So we are not going to allow this case. So this fourth case we will not allow at all. What is that? A equal to 1 and b equal to 1 case we will never allow. So always restrict the user from applying the input 1 1. You can apply 0 1 1 0 or 0 0. All the three cases are fine, but this is not allowed because of many cases. Like one thing is like it can store but it can't retain, it's very clear. But retaining again we can tolerate, but the problem is it is going to some unexpected result, right? So that result is not predictable, it is behaving something randomly, we don't know. So we don't need such a circuit, right? So that about it. Now let me tell you one more small thing. Say, Yeah, let me use this color. See here what is happening when both the inputs are like a equal to 1, b is equal to 0, you know that the circuit is giving me a 1, right? So when a circuit is giving me a 1, we typically call it as setting the circuit, right? Set means what? Setting the circuit. The circuit is set to a value 1, so that is the meaning. So similarly here the 0 1 case is actually what? Circuit is showing you a value 0 as a whole. I can call it as a reset case, right? So this is how I can reset a circuit, right? I mean resetting the circuit. So these two cases are important for me, so I'm calling like that. So can you tell me when this setting happens? Setting happen when this a is equal to 1 and definitely that b is equal to 0, fine. Similarly resetting happens when this a is equal to 0. So this a I can call otherwise as the set input. Okay, so in textbook and all you will see it like this, set input. Why I am calling this a as set input? Because when a is equal to 1 is helping me to set the circuit. So definitely the other input should be opposite to that. Similarly this b I can call it as the reset input. So the circuit I can reset by giving a 1 to this b. Okay, so here I can set the circuit by giving a 1 to a. So definitely the other input should be different because 0 0 1 1 are special cases, right? And this is something like so here there is no change, right? No change for the output. Here also there is no change for this output. So it's something like in the in computer you want to store some information, accordingly you either set or reset the particular device, right? Which is this device is capable of storing just a single bit, 1 or 0, fine. Now if you want to retain the information, means there is no power, like both inputs are 0. So that is the case when there is no power, still that information is retained in the computer memory. How it is possible? So this is a logic, right? When both inputs are like 0 0, it is retaining the information. So this is where the memory. So now only I can call it as a memory. So simply storing, it's not at all be going to be a memory. I can't use that term. Okay. Now this is something invalid for us. That means both inputs are 1, right? That is something prohibited for the whole circuit. So that about the conclusion that A input and B input, like what I explained so far, is now called as a set input and reset input, and this is the common output I am having. Right, and you can see that in all the valid cases, like this case 1 and case 2 definitely, and this case 3 also, all these things are valid, right? So what is coming here, this Q, you can see that here I am having its complement, right? Similarly here this is 0, see here you are getting its complement, right? The Q output, here also this is 1, here I am getting its complement. Here also this is my Q, and here I am getting its complement, right? So this is again an observation. If you take two outputs, like here in this all this diagram, I am taking a single output. Suppose I am taking one more output, say through that middle portion, I will get the complement of the other output. So now I am going to do that also. Like this is one of the output I am taking. Now another output, let me take as, so from here I am taking this output. You can use any path. So this will be something like a Q bar. Okay, so that's all. And so this is something for the building the concept I explained this way, but in the textbook and all you will be seeing this diagram. I mean this right side diagram is important. Same diagram only, we are just redrawing the diagram. Okay, this reset input and the set input, hope you remember so this is my first NOR gate, right? So the NOR gate 1 and the NOR gate 2. And NOR gate 1, the input is what we call as the reset input. Its output is given and the reset input is given to this NOR gate 2, right? Now the same two NOR gates I am drawing here. This is my NOR gate 1 and this is my NOR gate 2. Okay. Now this NOR gate 1, the input is the reset input. So I applied like this. See, the reset input I applied. Now for the NOR gate 2, one of the input is a set input, that also I applied. And now you can see that the output of NOR gate 1 is given as input to NOR gate 2. Output of NOR gate 1 is given as, input to NOR gate 2. See this feedback, fine. Similarly output of NOR gate 2, okay, let me use some different color for you. See this set input and reset input, that is clear for you right now. Let me tell you, See, the output of the first NOR gate is given as input to the second NOR gate, right? The NOR gate 1. The output of NOR gate 1 is given as input to NOR gate 2. Similarly, use a different color. The output of NOR gate 2, this QA, is applied as input to NOR gate 1. So, output of NOR gate 2 is applied as input of. So, like this. So, this kind of a circuit. So, it's simple to draw, right? Some kind of cross coupling. So, just connect two NOR gates and take the output of the first NOR gate and give us input to the second NOR gate, and take the output of the second NOR gate and give us input to the first NOR gate, and apply the reset input to the first NOR gate and set input to the second NOR gate, right? And from here you will get this QA, right? This output QA you will get from let's see that. Sorry, I made a mistake. This set input I applied it to this NOR gate 1. Okay, so this was my NOR gate 1 actually. Okay, and this was my NOR gate 2. Okay, now from NOR gate 2 I am taking this QA, and this particular QA I am taking from here. Similarly, from NOR gate 1 I am taking the QB. Okay, fine. So, the same circuit I drawn in a different way. So, just understand like that. The top one I am applying reset, and the bottom one I am applying set, like that. Okay, so this is the NOR gate implementation of a circuit that is capable of storing one bit of information. So, we observe different cases. So, this is something called as latching, just like the normal latch to a door. So, what happened is you taken something inside the room and you latched it, right? So, just like that you taken one inside the circuit and you latched it. So, here you are latching one. So, this case I can call like a, this case I can call that this is something like a latching binary information 1, and here this corresponds to latching the binary information 0, and here this corresponds to retaining. Whether you latched whether you latched 1 or 0, you are now capable of retaining that information. Okay. Retaining. So, that is what we seen. So, it resemble like the latch. So, that is why we call this circuit as a latch circuit, the basic latch circuit. So, this is what, this is the NOR gate implementation of latch circuit. And you should know that this is a default implementation. By default, if I say like I have a latch, so this by default it is nothing but the NOR gate implementation. Typically we call it as the set input and reset input, SR latch. Okay, so this circuit we call as the SR latch. SR latch. SR latch, the basic implementation is by the NOR gate only, but the same latch you can implement using NAND gate also. That you can think of it like what will be, where to apply this reset set, like that. Okay, so instead of the same way you realize a circuit, say instead of this NOR gate you use NAND gate and try to derive all the 4 cases. So I just want to know what is the set input, what is the reset input, right? And similarly what is the case for setting, resetting, no change, as well as see what is the prohibited state, if any. Okay, so that you have to try at your home, I mean as homework. We may see in the subsequent videos, but still you try it and come to the next video. So this is the final conclusion. So when I am having an SR latch, so this is my SR latch or RS latch, in any way you can say. SR latch, what I am having, I have a 4 different cases for the input. Both can be 0 0. This is no change case, right? So it will simply return 0 or 1 as it is. So that is the first case. So actually the first case we explained is setting. Okay, anyway this is one case. So this is when this R is equal to 1, that is resetting. So this corresponds to reset. Okay, and this is the case when S is equal to 1, R is equal to 0, and that corresponds to set, and this is something called a no change. And this 1 is something not allowed, okay, or prohibited, like that we call. Why it is not allowed? Understand that there is no issue when you apply 1 it will simply try to store that 0, but it is not capable of retaining that 0. That is actually what is creating the problem. That means once you take that input away, when you this set and reset was 1 1, then I taking it away means when both are like a 0 0, I am supposed to retain the previous information, but I am not getting it. Not only that, I am getting something undesirable, which is something unpredictable even, right? So that kind of a complication I don't want. Okay, so that is something not allowed in case of a typical SR latch. So this table is typically what we call as a characteristic table of the SR latch. For further latches and other devices, we will see this faster. So here I spent more time to help you to understand how it is working actually. I mean, in the textbook and all, you will see the diagram, the circuit diagram, as well as the characteristic table, and they may explain, and it will be difficult or hard for you to visualize things. So that is why I spend this much time to explain all the cases and sub cases. So those who gone through the video patiently might be able to understand, so why I spent this much time. So for others, it's enough to see this last part. Okay, you just in the exam point of view, they may ask you the circuit diagram and characters table. Finally, you have to give this. You can even by heart also, fine. But now you don't have to by heart. You know why it is happening. Suddenly, if I change the circuit, say with an AND gate, you should be able to tell the answers. That is the benefit of having this kind of an explanation, this kind of an analysis. So you also take, instead of NAND and OR gate, if you want to implement, you can implement latch using some other way also. Try it, okay, and see whether it is able to store as well as retain the information. That is our requirement. Then you are done. Okay, so that is our basic memory element. So this is something very, very fundamental for computer. So without this memory storing, nothing is possible. Okay. So basically our registers, memory, they are all made up of this circuit, latch circuit or its variation. So typically there is something called flip-flops that we will see. So that is nothing but a clocked latch. So with this we will add clock also. So that just triggering everything is something automatic. Yeah, that's all. Thanks for watching. See you in the next video.